Hello friends, welcome back to the session on DC distributor, the module 5 DC distribution systems. In the previous session we discussed about the DC distributors. We discussed about the different type of systems like 3-wire system, 2-wire system, and the different kind of distributors like ring distributor, and we also discussed about the balanced loads and the point of minimum potential and how important it is to have the distribution system in terms of DC, because we have got various loads like electromechanical works, and the most importantly the DC load is on the traction where the DC power is very much required. So when we have the DC distributor system, it is obvious that we need to design a system which is going to be reliable and less complex, and at the same time which is going to serve the purpose of providing the better efficiency in terms of distribution. So when we discussed about the DC distributors, we considered the different type of loads. In that type of load, we first considered the concentrated type of load. In the concentrated type of load, I explained you that what is a concentrated load, why a load is called as a concentrated load. In a simple example, I can say the concentrated load is nothing but a bird sitting on a transmission line. Concentrated load is a pointed load which is concentrated on a particular point. So a bird sitting on a uniformly distributed transmission line, or transmission line which is connected between the two poles, is considered to be the concentrated load. When the concentrated load is provided on a transmission line, if the supply is given from one end, what will be the voltage distribution, what will be the current distribution, we discussed about. At the same time, we also discussed about how to consider the unequal voltages which are given from both the feeder ends. Basically, the distributors are connected to the feeders are connected to the substations. Feeders are the one which gives the high power to the distribution lines, that is through the distributor, service mains will go to the consumer premises. So the DC distributors which are getting the power from the feeder, if it is connected only at one end, what will be the distribution of the voltage and what will be the current all across the transmission line, and where the minimum point potential occurs, we discussed about it. And going ahead, we also discussed that if both the ends are feeding the voltage and both of them are unequal, then what will be the current distribution throughout the transmission line, and how to consider the voltage drops and where exactly the point of minimum potential exists. We discussed with the help of the voltage distribution diagrams, as well as we plotted the current distribution diagrams. We consider the voltage drop that happens between the sections and how to distribute the entire current throughout the load. And we also learned basic understanding about the DC distributor is that the point which is, or the section which is very near to the feeding end, will have the maximum voltage drop, and then the point that is going away from the feeding end will have the minimum voltage drop. Going ahead with this, there is another interesting type of the load which is called as the uniformly distributed load. This uniformly distributed load is the one which is considered to be distributed equally throughout the length of the transmission line. For example, if the length of the transmission line is considered to be L meters, then the uniformly distributed load is represented like this. That is the load that is distributed equally, and if it is fed at one end, and this is how it is exactly going to look at. Here also we are going to consider two cases: a uniformly distributed load with one end supply, that is a distributor that is fed at one end, and what will be the uniformly distributed load if the distributor is fed at two ends. Under the two ends, we are also going to consider whether it is going to be the equal voltages or whether it is going to be different voltages. Let's consider the first example, that is the first case: distributor fed at one end. Figure shows the distributor. The current that is loaded here, that is the load, is I ampere per meter. The length of the total distributor AB is the L meters, and distributor is fed at one end. Since we are considering the two-wire DC system, we have to consider both the go and return. So it is a very important assumption that we are going to make it, because DC always has two polarity, that is the positive and negative. Then we are going to consider both the wires when we design the DC distributor system with the load. So the DC distributed load is of I amperes per meter. Load means it is a tapping, or it could be the current demand that is demanded by the distributor line, or when the line is feeding, when the feeder Distributor fed at one particular point is as shown in the figure, and let L be the length of the distributor, R be the resistance per unit length in ohms. If we simplify this diagram, we need to find out where is the point of minimum potential. We understood that the distributor is fed at one end, then we can consider it is to exist at the center of the distributor. Let C be the center of the distributor, and let's consider C at a distance of x from the feeding end A. And let's consider an elementary section to find out which is going to be the minimum point of potential. Let that minimum point of potential be located with the help of the elementary section dx. Let the total length of the distributor remains as the same, that is L. We can calculate the total voltage drop considering the feeding point at the one end, that is A. So considering this figure, then current tapped at the point C is nothing but equal to the total current minus the total current up to the point of C. The total current that is flowing in the distributor, and then the total current that is up to the point of C, whatever the current that is going to come will give the current tapped at the point C. That means simply if we say, if we apply the Kirchhoff's current law, if the feeder is at the point A, then whatever the current that is tapped at the point C will be the outgoing current. Whatever the current that is fed between the AC is going to be the incoming current. So we understand that the current tapped at the point C is nothing but the total current minus the total current up to the point C. Since the total length of the distributor is L, then we can say that I into L minus I into X, that is equal to, when we take out the common I into L minus X. Consider elementary length dx near the point C. The resistance of the wire is R, that is the resistance per unit length is considered to be in ohms. So here we are going to consider the elementary section resistance as R into dx. When we consider this, we can get the voltage drop over the length dx by differentiating it. dV is nothing but equal to I into L minus X into dx, because I into L minus X is the current that is tapped at the point X and the point C. So dV is the voltage drop in the elementary section. So dV is equal to the current that is flowing, that I into L minus X into dx. So when the voltage drop up to the point, we can find out this by integrating this I into L minus X into dx between the limits 0 to x. So when we integrate this, the voltage drop up to the point C, that is VAC, is nothing but equal to I into R into Lx minus x square divided by 2 volts. Let's consider this as equation 1, and this is, as you know, that this is very similar to the equation of the parabola, that is x square minus x square divided by 2. So we can find out the voltage drop up to the point of B by substituting x minus L, because we know that the total length is L, and up to the point C it is the x, that is the distance from the feeding point A. So the distance from the point B is going to be x minus L. Similarly, using the same steps, we can find out the total voltage drop. VAB is nothing but equal to IR into L square minus L square divided by 2. So IR L square, if we take out as a common, that is going to be 1 by 2. IR L square divided by 2. And this is going to be half into, we can write this as IL into XL, because XL is going to be the distance, and then VAB is nothing but equal to half into I into R, where I is nothing but the total current that is flowing through the length of the distributor, that is L, that is I into L. R is going to represent the complete resistance of the distributor wire, where it is nothing but X into L. So I is the total current fed at the point A, R is equal to total resistance of the distributor. From this equation 2, we can conclude that in a uniformly distributed load, the total voltage drop is equal to that produced by the whole of the load assumed to be concentrated at the midpoint. So in a uniform load, if we think this as a definition for the voltage drop, then we can say that here we can write we can plot the current diagram and the voltage distribution diagram. Current loading diagram shows that it is a uniformly distributed load fed at one end, and this is the total IL, that is the total current that is flowing through the distributor. And the voltage drop, the voltage will be maximum at this point, and then gradually it decreases when we move far away from the feeding point, and this becomes 0 at the point B over the length L. So same way, as we have derived the equation, and it looked very similar to the parabolic nature, you can So the parabolic equation I r L square divided by 2 is nothing but equal to I into R divided by 2. So exactly at the center of the distributor, we can expect the minimum point of potential in a uniformly distributed load. So this this diagram shows the current loading as well as the voltage drop diagrams for the feeder that is feeding at one end of the line which has got the uniformly distributed load. And we can also find out what is the power loss in this uniformly distributed load. Power loss is nothing but equal to I square R because it's a DC loss. Power loss is equal to I square R loss can be obtained from the elementary length dx, which we have considered in the first diagram. So the current at any point C is at a distance of x from x, that is equal to I into L minus x, total length minus x. So hence the power loss over the elementary length dx is nothing but equal to dp is equal to I square R, that is I is nothing but I into L minus x whole square into R into dx. When we integrate between 0 to L, the whole equation I square into, expand this equation, L square minus 2lx plus x square into R into dx. Simplify the equation and integrate it between the limits 0 to L. We will get the equation P is equal to I square R L cube divided by 3 watts. So this is the total power loss in a uniformly distributed load fed at one point, that is fed at one end. Now let's consider the second case, distributed load fed at both the ends. When we think about both the ends, the voltages that are fed at both the ends could be equal or it could be unequal. Let's consider case by case. That is, the first case is ends maintained at the equal voltage. As the name itself says that both the voltages, that is the voltage that is fed at point A and point B, are going to be V volts, that are going to be equal voltages, and it is a uniformly distributed load over the length AB, and the current loading that is given is I ampere per meter. Total length of the distributor is L meters. And with this we can simplify the diagram, and we need to consider the point of minimum potential. Let's consider an elementary section dx at a distance x from the point A. The total current that is to be supplied is going to be I into L amperes because it is the uniformly distributed load. As both the ends, two voltages are equal, each end will supply half of the voltage. That is, each end is going to give the required current of IL divided by 2. And C is going to be the midpoint, and let's consider this as the minimum point of potential. The point of potential, let's consider it as it is at a distance of L divided by 2, and it is at a distance of x meters from the point A, and the current that is entering at the feeding point A is IL divided by 2. The current at the point C can be written as, the current at C is nothing but incoming current is IL divided by 2 minus the current in the section is I into x. So if we simplify this equation, I into L divided by 2 minus x. Now to find out the point of minimum potential, let's consider the elementary section dx, and the resistance of the elementary section is R into dx. So now we know the resistance, we know the current, so we can find out the voltage drop over the length of the elementary section dx as dV is nothing but equal to I into R, that is I is nothing but the current that is flowing, and the I is I into L divided by 2 minus x into R into dx. Hence the voltage drop up to the point C can be found out by integrating the IR between the limits 0 to x. So VAC is nothing but equal to, when we substitute the values I into L divided by 2 minus x into R into dx, it will become IR into Lx divided by 2 minus x square divided by 2, because we are integrating between the limits 0 to x with respect to dx. So now the maximum voltage drop is at the minimum midpoint, and that is at the minimum potential point of potential, and in this case it is at L divided by 2 because both the feeders are feeding the voltage at the midpoint. We can expect the minimum point of potential, and maximum drop that we can find out with respect to the length, that is L divided by 2, IR into L divided by 2 into L by 2, because when we see here Lx divided by 2, x is nothing but L divided by 2, here L divided by 2 into L divided by 2 minus x is again L divided by 2 whole square divided by 2. Simplify this equation, we will get maximum drop is nothing but equal to IR divided by 8. We need to remember this equation because when we